Our first presentation for tonight is called Can Great Programmers Be Taught? Our speaker is John Ousterhout, who is the Bosak Lerner Professor of Computer Science at Stanford University. His current research focuses on new software stack layers to allow data center applications to take advantage of communication and storage technologies with microsecond scale latencies. Ousterhout's prior positions include 14 years in the industry, where he founded two companies, Scriptix and Electric Cloud, preceded by 14 years as professor of computer science at UC Berkeley. He is the author of the book, A Philosophy of Software Design. Actually, this is how I got to know about him, and this book is amazing. I recommend it to anybody who's in the software business or who's running software businesses to purchase it and maybe make it as a must read for all the people working with him. He is also the creator of the TCL scripting language and is well known for his work in distributing operating systems and storage systems. Ousterhout received a Bachelor of Science degree in physics from Yale University and a PhD in computer science from Carnegie Mellon University. He is a member of the National Academy of Engineering and has received numerous awards, including the ACM Software System Award, the ACM Grace Murray Hopper Award, the National Science Foundation Presidential Young Investigator Award, and the UC Berkeley Distinguished Teaching Award. Professor, feel free to take over the presentation. I will stop sharing right now.
All right, thank you very much for that introduction. First, before I start, I would be happy to take questions and comments during this talk as well as at the end. In fact, I'd suggest you might as well ask a question in context rather than wait until the end when we moved on to a different topic. I'm hoping that this Zoom meeting will allow people to raise their hands. Their blue hands. I don't know if that's possible. Dragos, is that enabled? Or if not, I would say
yeah.
If not, I would say either chat your question or just chat the word question. I'll try and keep my eye on the chat screen, and then I'll stop and call on you. Or for that matter, you could just jump in and interrupt me. I won't be upset by that. So anyhow, please feel free to, I think I'm going to say some things that you'll want to respond to. So please do respond at the scene of the crime. So let me share my screen. Nope, that's not the one I wanted to share. Sorry. Okay, try again. There it is. Okay, hopefully you can all see my title slide saying, Can Great Programmers Be Taught?
Yes, we do.
Some background on this. So people have been programming computers for 80 years or more, and yet we still have little agreement on software design or what good programs should even look like. In fact, there's not even a lot of discussion about that. And so in this talk, I want to talk about things I've been doing to try and increase design awareness in the software community. But first, let me start with a couple of thoughts. These are sort of things that have been rattling around in my brain for a decade or more and that have triggered this work. So the first one, and actually this is a question for you. What is the most important concept in computer science? So if you had to pick one thing, one idea that threads its way through all of computer science, whether it's systems or theory or graphics or HCI or AI or architecture, what's the single most important idea? So help me out here, just chat in the chat window some thoughts about this. Most important concept in computer science. Abstraction, being understandable for humans, the CAP theory. Users. Readability, okay, these are all good ideas. Others. Managing complexity. That one's very close to my heart. Working code, understanding the problem. Great, all great ideas. Writing testable code. Okay, so what I would say is actually more along the lines of abstraction. To me, the most important idea in all of computer science is the notion of problem decomposition. That we take a big complex problem and we chop it up into pieces that can be solved relatively independently. And abstraction is a way of dealing with that. And the reason we do that is to manage complexity, which is one of the other comments that was made. And when I asked Don Knuth this question, he said layers of abstraction, which I thought was almost correct. Although given that Don Knuth said it, maybe that makes it correct by definition. Anyhow, for me, it's problem decomposition. And yet we don't teach it. I know of no course, well, except for the one I'm going to tell you about, that attempts to teach problem decomposition as one of the fundamental core concepts of the course. And by the way, if you know of a course that does that, I'd be curious to hear about it. If not now, you can drop me an email. So that's the first thought. And I've been wondering why, how can it be that the most important thing in computer science we don't teach? Then the second thing is, it's well known that the best programmers are way more productive than other programmers. Easily 10x, in fact, Google coined the word 10x programmers to describe them. And yet, as far as I know, no one teaches the skills to become an elite programmer. In fact, I'm not even sure we have agreement on what those skills are. And these are the two thoughts that I had been noodling over for, probably a decade or two. And wondering, how can this be? So then the next set of thoughts after that was, well, can we teach great programmers? Is that something that can be taught, or is this just an innate skill where either you have it or you don't, and if you don't have it, you can't learn it? And then many summers ago, I read a really great book, which I recommend to you if you haven't read it. It's called Talent is Overrated by Jeff Colvin. And in this book, he goes through example after example after example in a huge number of different areas to show that the most important thing that separates great performers in a field from the average performers is not, there's no evidence of any sort of inborn talent. It's all about how much practice they've had. That's the one thing that correlates with excellence. Now, of course, if you're not 6 feet tall, you're probably not going to be an NBA basketball player. So there's some innate stuff. But in most of the fields, particularly the cerebral fields, it's all about practice and learning. And so when I read that book, I thought, well, then it must be possible to teach programming skills. This can't just be something that's innate. But then the next question is, well, who's going to do it? And the problem is that by and large, faculty don't really know how to code. When you're a graduate student, you do some coding, doing your dissertation, but your professor doesn't really know how to code. In fact, graduate students typically look down on their professors as really bad coders, which is interesting because they're going to turn into those people in a few more years. So the faculty don't know how to code, so they can't teach their graduate students. There's nobody to teach the graduate students. And then when a graduate student becomes a professor, the first thing they decide is they don't want to code anymore. And so whatever learning they were doing, it stops. And so our faculty are by and large unable to teach programming skills. However, I consider myself an exception to that rule because I love to code. Coding is one of the things I live for. It's just one of my favorite activities in life. And I love software design, the notion of how you build systems and decompose problems. And so over my career, I have written, I'm guessing 250 to 300,000 lines of code I've coded. And if a year goes by where I don't write 5,000 or 10,000 lines of code, I feel like it was not a good year for me. So I figured if anybody can do it, it's probably me. There probably aren't many other people better positioned than I am to do it. And plus, I had a couple of stint in industry where I started a couple of companies, neither terribly successful, but I learned a lot about building software in the process. Then the third question is, well, how would you teach this? And I noodled over that for a while. And finally, I decided there's really only one way to answer all of these questions, and that's just to try teaching a class. So I did it. I started a new class at Stanford. It's called CS 190, Software Design Studio. We're now in the 6th offering of that class. In fact, one of the reasons I was rushing to get back here for this is I was just teaching a class this afternoon. And CS 190 is taught not like a traditional computer science class in college. It's taught more like your high school writing class, or at least like my high school writing class, where the way that worked is we would write something and then the teacher would read it and cover it with red ink, and then we'd revise it and the teacher would read it again and cover it with more red ink, and we'd iterate this process a few times. And the key elements of this, I think, are iteration and feedback, getting criticism so that you can see the problems, hear about why those are problems, then have a chance to revise and see that the revision actually makes things better. See how when you fix the problems, things get better. I think this is how you learn. But of course, we don't do that in any of our existing computer science classes. In fact, most classes give no feedback at all on actual quality of code or design. Some do, but even in those classes, typically the student gets feedback and then you go on to the next project. There's never an opportunity to iterate for the students to see how much better their project would get if they had the feedback and rewrote it. So CS 190 is taught like an English class. It's taught in 3 phases. The first phase, which we're just starting this quarter, students have 3 weeks to build the largest system they can possibly build from scratch. It's typically 2,000 to 3,000 lines of code. Then we do intensive code reviews. I read every line of code from the students. It's a small class, but that means I have to read 20 to 30,000 lines of code in 1 week. It's a pretty crazy week for me. So we do code reviews where I read all the code, students read parts of each other's code. We do code reviews in class. I meet for an hour with every team to go over the code reviews. And then they go back and they revise based on the code reviews. Then we do another round of code reviews based on the revision. And finally, in the 3rd phase, students start a whole new project and build another system from scratch. So they get 2 opportunities over the quarter to design from scratch. And then there's a final round of code reviews at the end. So this is an extremely tight schedule. The class, I think, would be better in a semester rather than the quarters we have here at Stanford, because we could do an extra project and not be quite so rushed. But this is how the class works. So it's iteration and feedback. So then the next question, which you're probably wondering, is what are these magical secrets that make people great programmers? Well, first, I don't claim to have a magic formula. I have some ideas, things I've thought about over my career that I think I've learned from writing code and reading a lot of other people's code. But I don't claim to have the final word in this. These are my current ideas. And so the class is based on about 5 or 10 so philosophical concepts. They're so vague. They're really more like philosophy or Zen than recipes you can follow or precise instructions. And I've listed most of them on this slide. I'm going to talk about the ones in red. So things like classes should be deep, define errors out of existence, or strategic versus tactical programming. And these are pretty vague. And honestly, I think they're too vague for students to immediately apply them. But what does work is to tell the students about this, and then they write code. And then we do code reviews. And in the code reviews, I can show how, oh, that class you wrote, it's not deep. And here's the problem with it. And here's how to make it deeper. And through that process of iteration, then I think students can start to grasp what the concepts are like and what they mean. And the other really important thing is that there are a lot of red flags in the class. So these are things I can tell students about that if you see this means you probably have a design problem. Not always, but it's a pretty good indication of the design problem. And if you can become good at identifying red flags in your code, then you'll be able to design reasonable code, because if nothing else, you just try a random collection of ideas until you no longer can find any red flags, and you'll probably have a pretty decent design. So I think red flags are really, really important in designing good code. So anyhow, these are kind of the basis of the class. And as I said, I think they work best in the context of writing code and getting code reviews. I see a question, what does deep mean in this context? I'm going to come back and explain that in the next slide. So let's talk about these concepts. The first one, maybe the single most important one, is the notion that classes should be deep. And let me explain what I mean by that. So if you think of a class as a rectangle, where the area of the rectangle represents the useful functionality that class provides, whatever functions it provides, and then the top edge of the rectangle is the interface. And the interface is everything that a user must know in order to use the class. So it's not just the function prototypes, but it's side effects or tricky things or everything that somebody really needs to know in order to use that class. Okay, so if you think of a class that way, then if a class has not very much functionality and a lot of interface, that's a bad class, because interface is cost. That's what people have to learn. Now people say, well, interfaces are good, and they are good, but smaller interfaces are better. So what we want to do is we want to maximize the benefit and minimize the cost. A shallow class with not much functionality and a lot of interface is bad. It maximizes the cost and minimizes the benefits. Instead, what we'd like is a deep class. That is one with a really small, really simple interface that still provides a ton of functionality. And by the way, this notion of depth, this is just a reformulation of something David Parnas published in a classic paper around 1970 called On the Criteria to be Used in Decomposing Systems into Modules. By the way, it's one of my two favorite papers in all of computer science. If you haven't read it, it's still topical today. So classes should be deep. Unfortunately, they are often not deep. By the way, this applies not just to classes, but to methods, applies to larger things like modules. All of the objects should have small interfaces while providing powerful functionality. So I see methods like this all the time, both in student code and in code I've seen in industry. If you look at this method hides nothing. In order to use the method, someone pretty much has to know exactly what goes on inside the method. The implementation is the interface. And furthermore, the irony of this is it takes more keystrokes to type out the invocation for this method than just to type out the body of the method. You have to do more work to use the method than if you just did what the method does. It's crazy. But methods like this occur all over the place. And I bet every one of you has seen methods like this. So the problem with this is there's a common fallacy. And by the way, we teach it in our classes right now. The fallacy is that classes and methods should be small. And one of the main embodiments of this is, many of you have probably seen a book called Clean Code by Robert Martin that takes this to the extreme. He says the only thing better than a small class is a smaller class. Your method should be so small that if it has more than one control statement like if or for, you should divide it up into multiple methods. In my opinion, this is crazy. This results in, if you take this to the extreme, this results in what I call classitis. Classitis is what happens when somebody hears classes are good, but they thought what they heard was more classes are better. And so they try and have as many classes as possible, where each class adds the smallest possible increment to what previous classes have had. So you end up with an enormous number of classes. So a sad example of this is the Java world, where classitis is rampant. It's become part of the culture of the Java world, have as many small classes as you can. For example, until a few years ago, if you wanted to open a file in order to read serialized objects from it and you wanted buffering, you had to create 3 different classes to do that. One for the basic file, which does essentially nothing, then another one to add buffering, and another one to add deserialization capability. To me, that makes no sense at all. Why should every single person have to create an extra class for buffering when you know 99.999% of all users will want buffering? Instead, the default should be that the file stream class should support buffering. And then you may want to have an option to disable it if people don't want it. But the classes should do the things that are most common. So I would argue length is not the primary issue. It isn't small versus big. It's abstraction. Are we hiding complexity? Because deep classes, these give us leverage against complexity, where you can take a relatively complicated thing, all this functionality, and hide it behind a really simple interface. So people see something simple and they get something that's actually internally very complicated. That's abstraction, and that's the key thing. And so the most important thing is to design classes, methods, functions, modules that are deep. Then, if they're long and they feel uncomfortably long, awkwardly long, then see if you can divide them up into multiple things. But each of those individual things you divide it up into better be deep. Dividing into a bunch of shallow stuff doesn't provide much benefit. So here's an example of a deep interface. This is by the way, my favorite interface in the world. File I/O in Unix and Linux. This is a truly beautiful, rich, deep interface. There's only 5 functions: open, close, read, write, seek. Well, I/O control, that's a 6th one. And most people don't even use seek. They just open, close, and read and write. And all of the interfaces are just falling over simple, except that the flags argument to open has a little bit of complexity to it. The flags interact in some slightly funny ways. Dead simple. And yet there's an enormous amount of functionality implemented behind this interface. You know, it's order hundreds of thousands of lines of code in the kernel. How do you manage disks and allocate blocks? And how do you organize directories and do path lookup and permission management, security and scheduling, all this stuff. There's an enormous amount of complexity, but this incredibly beautiful, lovely, simple interface. So that's an example of a deep class. Okay, so that's deep versus shallow classes. Before I go on, let me just pause briefly. Questions on this or expressions of disbelief? Think this is a bad idea? Any thoughts from those of you out there?
I got a thought, John. So if this classitis, sorry if there's my kids screaming, but if this is so prevalent, this classitis, how do you fight it in the workplace or when you're applying for jobs? Like if you write deep classes and people think they're bad, they're going to therefore perhaps think your programming is bad. Do you try to convince every person you come across, or what do you think the way forward is there?
So I would argue to push as hard as you possibly can. You know, in any given situation, there are limits to how hard you can push. I'm going to come back and talk about this later on too, in terms of how do you create more of a culture of design in companies, because a lot of companies don't have that culture. So let me defer that because I'm going to come back to it. But I would say judge how much you can push, and then as you get more senior and hopefully have more credibility, then you can start advocating more strongly and try and get other people to do it as well.
I have another question.
Yes.
This is, let's say the open function that you just said has 10,000 lines. Putting them in the same place wouldn't be maybe a nightmare to maintain such a code? Wouldn't be easier to maybe split in multiple classes and put functionality in different places just to allow to be maybe more maintainable?
That might well make sense. Yep, if a function gets really long, I would look for ways to split it up, but I would not expose that split to callers. I would not do that. I would make that internal to the function. Yeah. And again, only do it. It only makes sense to separate things if they're independent. If they are dependent, I have a phrase that you call conjoined functions, where people split something into two functions, but you can't understand either function without reading the other function in its entirety. If you do that, there's no benefit in splitting those up. In fact, you've actually made things worse because you have these related things that are not near each other. So it's hard to see them both at the same time. So it's all about figuring out which things are independent and which things have dependencies.
Thank you.
Okay, let me move on. Next, I want to talk about define errors out of existence. This is another area where the way I think about things is a little bit different, I think, than what people are often taught. So exceptions, I think we all know, are an enormous source of complexity. Often, they're one of the main things that makes projects hard to maintain and hard to understand, because fundamentally, they break the normal flow of things and they happen at unexpected times. So the common wisdom out there is program defensively. Detect and throw as many exceptions as you possibly can. The more exceptions I throw, that must mean I'm being a defensive programmer. So I'm a better programmer if I throw more exceptions. Well, I disagree with that. Now, exceptions are essential. You can't get rid of them all, but I would argue that you should design code to minimize the number of exceptions that people have to deal with. And in particular, there are many situations where you can define your semantics in a way that completely eliminates an exception by simply making the exception, just handling that as part of a normal case. So there is no longer an exception. And I would argue when you can do this, then this is reducing complexity in your system. So I have three examples I'd like to go over. The first is in the Tcl scripting language, the unset command. So when I was writing Tcl and I implemented a command called unset, which deletes a variable, I thought, it's a mistake, by the way, I thought no one in their right mind would ever try and delete a variable that doesn't exist. So I'll throw an exception if the variable doesn't exist. Well, it turns out I was wrong about that. In fact, people delete variables that don't exist all the time. The classic case is you get halfway through doing something and you decide you want to quit and you want to clean up after yourself. And so you go through and delete all the variables that might possibly have been allocated, but not all of them were actually created yet. And so this is so problematic that, in fact, it's become an idiom in Tickle that basically whenever you invoke unset, you always wrap it in a catch command that will catch any exception and throw it away. So that's bad. That's just adding complexity to people. What I should have done was to change the definition of unset ever so slightly so that it's not deleting a variable, because that implies the variable exists. Instead, unset makes a variable not exist. And then if it already doesn't exist, you're done. That's just part of the semantics. It's no error, nothing to throw, everything is fine. That's what I should have done. Another example in Windows. I can't remember if this is still true or not, but for many years, you couldn't delete a file if someone had it open. That would throw an exception. And I don't know how many of you have been through this where you try and delete a file, you can't, it says file in use, and then you go around and you think, oh, who's got the file open? And you start closing applications, hoping you can find the application that has the file open. And sometimes you can, and other times you can't. I would end up rebooting the system just so I could delete this file. And then I would discover, actually, it was the daemon that had it open, and the daemon restarted when I rebooted the system, so I'm still stuck. Unix has just a lovely, lovely definition of this. In Unix or Linux, if you delete a file, the file appears to go away. You know, the directory entry is deleted, there's no sign of it in the system. But in fact, if someone has it open, the file stays around, and it stays there until it's closed for the last time. And then once it's finally closed, then Unix will clean up the file. That's a perfect example. It just defines all those errors, takes all those errors. There are no longer any errors. I mean, an alternative would have been to delete the file and then throw errors for anybody who had the file open. But that would have created an enormous number of additional exceptions for people to deal with. And so in Linux and Unix, Ken Thompson and Dennis Ritchie, they just got that right. So eventually, I believe Windows added an option where I think maybe when you open a file, you can specify that it can be deleted while it's open. I forget what happened. But so they sort of partially solved the problem, but they didn't delete the directory entry until the last time the file was closed. So if you wanted to make a new file, like you want to rerun make and rebuild something, you can't do that because you try and write a new file. Now that name is locked down. You can't create a new file in the same spot. So they still missed and ended up with these extra exceptions. And then finally, my third example is the Java substring command. So substring in Java throws an exception if you specify indexes in the range that are out of range for the string. And I found that's just a huge source of complexity because I end up having to write code that clips the indexes to the range of the string before I call substring. And if I forget to do that, then I get a runtime exception that causes the application to crash. To me, this is another classic case where they should have defined that exception out of existence. That is, change the substring command so that it returns any characters in the string that overlap the range you have specified. And so if you specify a range outside the string, there's no overlap. It's very clean and simple. If the range partially overlaps the string, again, you return the overlap. So these are all examples. Now I will say you can't always do this. When I teach CS 190, there are invariably, when the first project is turned in, there'll be one group who has not implemented any exceptions at all in the project. In fact, they have no error checks. And I say, shouldn't you be checking for errors here? And they say, oh, we just defined all the errors out of existence. And then I say, well, actually, you didn't define them out of existence. You simply ignored all of these cases. So, not all errors can be defined out of existence. But whenever you get a chance, I would say do it. And the goal is, I would argue, minimize the number of places where people have to handle exceptions. That should be the goal. Can't make it go to zero, but only do it when it's really important. I'll pause briefly. Comments or questions or disagreement about that one?
Nobody likes exceptions, so I think
they're better than the alternative, but there's all these things in computer science where X is good, but more X is not better. And exceptions are one of those.
I think something related to this, which I see at my workplace, is to make it impossible to define or to have bad input. That is, instead of like having various combinations where only some combinations make sense, you link them together somehow depending on the programming language so that you can't specify something that's wrong.
Yeah, if you could do that, that's great. Again, you've basically taken special cases and errors out of existence. By the way, I should say there's two ways you can deal with complexity in large systems. One way is through abstraction or modularity, which sort of hides it. And the other way is just to get rid of it. And things like this just eliminates the complexity. It's gone. You don't have to hide it. It's nowhere in the system. So that's the best. Okay, rolling onward. Now I'd like to talk about tactical versus strategic programming. So in tactical programming, by the way, is probably what most programmers do most of the time. In tactical programming, the goal is you want to get your next thing done as quickly as possible, whether it's a bug fix or a new feature. And it's sort of hard to argue about that. After all, isn't the whole goal of computer science to make things work and fix bugs? So shouldn't we be trying to do that as quickly as possible? But the problem with tactical programming is that in the back of your mind, you say, well, yeah, I want it to be clean. Yeah, I do. But, if there's a little tiny thing here or a little kludge there, I access a global variable here, that's okay if it helps me to get this next thing done quicker. And the problem is that those little things just pile up at a furious rate because everybody in the project is adding a few of them for everything they do. And you have dozens and then hundreds and then thousands of them. And then even worse, the problem is it's almost impossible to get that complexity out of the system once it's in there because there's not one thing you can go and fix. Complexity does not come about because you make one huge tragic mistake. You make a whole bunch of little errors that add incremental complexity. And so if you want to defeat complexity, by the way, you have to sweat the details. You have to sweat the small stuff. So lesson number one, complexity is incremental. Now, there's an extreme form of the tactical programmer that I call the tactical tornado. I bet if any of you have been in a commercial organization, I bet every one of you has seen this person in action. Maybe some of you actually are tactical tornadoes. Hope not, but tactical tornado is the extreme tactical programmer. In fact, bosses often think these people are heroes. If something needs to get fixed right away, call in this person. They'll get it done faster than anybody else. And what they do is they do an 85% solution that just leaves a wake of destruction behind them that other people have to come along and fix up. And it's sad. Like I said, it's sad. In some organizations, these people are actually heroes. And then the people that come along and clean up after them, their bosses say, boy, it doesn't seem like you're making very much progress. What's going on? Well, it's because I was cleaning up all the messes from this other person over here. So I think it's really important. If you want to have good software design, you have to accept the idea that working code is not enough. Yes, of course, code has to work. That's not enough. Instead, I would argue you should program strategically. And in strategic programming, the idea is the overall goal is to produce a great design. That's the long-term goal. And of course, the system has to work. Of course, we have to, but we have to produce a great design. And the reason for that is that that's going to simplify future development. That'll make things go faster. It may make us go a little slower today, but it'll make us go a lot faster in the future. And so that means you have to think about complexity, minimizing complexity, and you have to sweat those details. Don't let those little bits of complexity creep in. Another way of saying this is it's an investment mindset where you take a little bit of extra time today, but you get payback in the long run. So for example, in this graph, this is a totally made up graph. By the way, I don't have numbers for this. In the tactical approach, you go a little bit faster, you have higher slope in terms of your progress initially, but then as the complexity builds up, you go slower and slower and slower. In the strategic approach, you go a little bit slower at first, and complexity still builds up. So, the slope gradually drops. That fundamentally, eventually complexity will build up. But after a while, you actually have made a lot more progress than if you program tactically. Now, the really interesting question here is, which I don't know the answer to, is where's the crossover point? How far out? Is it after a month, 6 months, 5 years? And I don't know the answer to that. I would love for if somebody had evidence about that, I'd love to know what it is. My suspicion is that the crossover point is somewhere around 6 months. It's kind of at the point where you've completely forgotten what you did when you were writing that piece of code. And so you're coming to it new. And so if it has a bad design, you can't maintain it. Even yourself, even if you wrote it, you struggle to maintain it. That's just my opinion. If anybody has ideas about that, I'd love to hear them. So the really tough question is, how much should you invest? This gets back to the question I think that Matt asked earlier on. And if I look around at startups in Silicon Valley, most of them are completely tactical. They think we've got to get that first product out fast. You think we can come back and clean it up later. And you think if we're successful, no problem, we'll get a lot of money from VCs or selling stock. We can hire a whole lot of programs. We'll come up back and clean up our mess. And so these people are explicitly not worrying about keeping things clean. And so the code base becomes spaghetti instantly. And the problem is it's extremely difficult to repair this later on. I'm not actually sure that you actually can repair it later on. With however much you invest, not clear you can go back and fix the damage. Facebook is a classic example of this. They even wrote it into their corporate culture. Many of you probably heard the culture at Facebook. What they told everybody is move quickly and break things. And boy, they did both. And so in some ways, actually, developers loved this. It was so empowering that new developers would come in. They were expected to commit to the working website within their first week. Some of their code could be running on Facebook's website. And the code base became notorious in the Valley as incomprehensible, unstable. I had a couple of students who did an internship at Facebook one summer, and they'd been complaining about me making them do things like write comments and stuff in their code. And they came back the summer saying, John, we get it now. We get it now. He said, every Monday, they push a new set of code that everybody has to use, and nothing works again until Thursday. And so you have a day and a half to try and make progress before they push new stuff next Monday. You wouldn't believe it. So as you may have heard, Facebook eventually changed their mantra a little bit to move quickly with solid infrastructure, implying that, try and minimize the damage. And my understanding is they are trying to go back and do better design. But again, it's really difficult to do that after the fact. So as a counterexample, though, there are companies that succeed with a very strong design culture. Both Google and VMware had really strong design cultures, particularly when the formative years between 2000 and 2010. They were known as the places where people who like to build difficult but really clean software would go to work. And as a result, they were able to attract all the best engineers because good engineers don't want to work on crappy code. So for companies thinking about whether to be tactical or strategic, I'd say the reason you want to be strategic is because the best way to get code developed fast is to get good programmers, because we know about this 10x difference. And if you want good programmers, you've got to have a design culture. And by the way, as programmers, I would say vote with your feet. Try and figure out the design culture of companies before you go work for them. And don't go to work for companies with a bad design culture. You don't want to fix spaghetti code. So again, how much to invest? I don't have a precise answer on that, but I think the way to think about this is don't be heroic. You're not going to do some monstrous rewrite the whole software system tomorrow thing. Instead, you should be thinking in terms of continual small investments. Thinking about design always in little bits. And I think the right amount to think about is maybe a 10 to 20% overhead. So your current feature or schedule extends by 10 to 20%. But over time, you'll soon be operating at least 10 to 20% faster. And so then you'll have a net gain. And so this means when writing new code, think a bit about the design and take time to write good documentation. When you're changing code, I think the way people often do this is they think, I want to change the fewest number of lines possible because I'm afraid I'm going to break something if I change more than that. But that's guaranteed to be tactical, adding complexity. Ideally, what you should do is after you've made a change, the system should have the structure that it would have had if you had known from the start everything you know today and had just been able to build it with all your current knowledge. That's what you'd like it to end up being. Now, that isn't always possible. You discover something's really broken. It needs a massive overhaul. And realistically, you're just not going to be able to take time to do that right now. But I would say, whenever you change anything, always find something to improve. Always find something, some little thing where you're making the design better. Because the thing is, there's a good chance you're making something worse. You just don't know about it. And so if you even want to break even, you have to make something else better. So always just be constantly making little improvements. And the great thing about this is you can do it in a way that nobody else in your company will necessarily know, so they won't be yelling at you for taking too long. You know, if you take 3 times as long to build something, people may get upset at you. But if you take 10 to 20%, nobody will notice. And so what the question I would ask, in fact, if there's any managers here, I would say ask them, and if you, or go to your managers and go to your VP of engineering and say, are we investing in design the most that we can afford to do? Is this really the best we can do? And then look them in the eye and just pause and wait for an answer and see what they say. And my guess is almost any organization could afford something at the 10 to 20% level. I suspect a lot of organizations, most organizations today are not doing that, but I think they can afford it. So just feel out your management, agitate as much as you can in your company to do better design. Let me pause briefly. I have just a couple more slides after this, but let me pause briefly if there's any questions or comments on this. What do I think about open source software? In general, it would have a better design. Yeah, you know, well, I think there's good open source software and there's not so good open source software. A lot of open source software is just sort of extremely chaotic, let anybody do anything they want to it, and it tends to have a bad design. But there are examples that are good. Like, I've been doing a lot of work in the Linux kernel, and by and large, it's pretty decent. I would say pretty decent design. It's woefully underdocumented, which is ironic given how many thousands of people need to learn the Linux kernel. You'd think the documentation would pay off in spades, but the design is not bad. So I think open source software doesn't have to be poorly designed. Okay, let me go through my last couple slides, and then I'll open it up for questions. So is the course working? You know, it's kind of hard to know. I'd really have to come back and ask the students in 5 or 10 years. Realistically, you can't become a great programmer in 1 quarter. What I can do is get people started, to give them ideas they can think about becoming a great programmer. But what I do see is the class has a really great energy to it. And I can see that the discussions change in nature over the quarter. The first code review, students are pretty tentative, afraid to criticize each other, kind of feeling their way through. And by the last code review, it's just they're letting it all hang out and arguing about what features may make a system more complex versus simpler. And people are having discussions in class about that. And it's clear that students think about code in ways they never thought about it before. So that's great to see. The class has also been really interesting for me personally. And one of the reasons I don't actually mind having 3 weeks each quarter where I have to read 20 to 30,000 lines of code, it's really interesting for me to look at the students' solutions. They all solve the same problem. And so I get to see 9 solutions of the same problem. And it's really interesting to compare them and see which ones were more complicated and which ones were simpler. And why is that? What explains that? And so my ideas about software design have actually changed since I started teaching the class. And one particular example of that is this question about when you design something for the first time, should you make it specialized for what I need today, or should I do something general purpose? Really interesting question. And I initially thought, well, don't incur the complexity of the general purpose design until you know what you need. So start off with something relatively specialized, and then you can come back and make it more general purpose later if you need to. But as I looked at students' projects, I found that all the specialized approaches were super complicated because they end up sort of specializing the low-level classes. The user interface concepts would feed their way down into the database because everything was specialized to do one thing. Whereas the general purpose classes were really simple and deep. And so I changed my mind on that. Now I realize the way to build classes is you should make them somewhat general purpose. You know, don't go overboard, but try and build your lower level classes so they could potentially be used for more than one purpose. And that was just something that came from reading student projects. So after I taught the class once or twice, I started giving talks about the class like this one, and people said, you should write a book about this. So in 2017 and 2018, I had a sabbatical, and I did. So and the goal was to try and capture those ideas, hoping to reach more people, also hoping to maybe start more of a discussion in the software design community. And then also, I wanted to help create a vocabulary that people can use to talk about software design. That might help. That this notion of deep versus shallow classes, now you can look and say, well, this class is a lot shallower than this other class over here. Or you can start snickering behind the backs of the technical tornadoes and talk about in your organization about that. Or, sneak in at night and put a little tornado sticker on their door for them to see when they come in the next morning. So it's a short book, only about 170 pages. It's like the things I had on an earlier slide, it's more philosophical than prescriptive. And it's been out for a couple of years. I have worried about the book that, like the class, the ideas don't really make sense standalone, that you need code reviews to really get them. But I'm hoping that perhaps the book could be a companion to help people do better code reviews and use that to guide discussions. So just to wrap up, I'm totally convinced that software design can be taught now. The current class, unfortunately, is not scalable. I can teach 18 people a year. That's it. So next step would be to try and somehow figure out how to scale it, but I don't know how to do that. I feel like principles are emerging. I feel comfortable with the principles. It's possible I'm wrong on some of these, and I'm always interested in hearing feedback. If you think I'm wrong on any of these, or you have other ideas for principles, I'm really interested in hearing about them. And long term, I'd like to find a way to somehow increase the overall sense of design awareness in our community. I'd hoped the book would do that. I haven't gotten a lot of feedback. We have a mailing list about the book, but it's not a heavily trafficked mailing list. If you have things you want to talk about, feel free to join in. And my plan is to incorporate new ideas as I hear them into the future versions of the book. I have a few new ideas, nothing super radical yet. And overall, the question is, can we agree as a community on a set of design principles? When I started on this, I wondered, is it possible that there are many good designers and they all work with different principles, and the principles are all good but totally different, and there is no one set of principles? I don't think so. I think that there really are universal principles, and I think it'd be really cool if somehow as a community we could start agreeing on those and find ways to teach them to more people. All right, so that's the end of my slides. So I run a little bit long there, but I'm happy to take questions as long as, Dragos, you feel it's appropriate before we should move on to other things.
No worries, everybody's home, so we can go ahead and take some questions for sure.
I have a question actually. You talked about the sort of design role, and I'm wondering, are there people with specific with that goal in mind? Like obviously you've got your manager or whatever is focused on getting a product out or something like that, but is there somebody on the team with that specific role or responsibility to help push the almost the stability of the code, the sort of structure of the code, to ensure that it's stable, not just, and then those two people would discuss and figure out how to balance between those two goals? Or is it mostly production focused?
I think it varies a lot from organization to organization, but I know there are plenty of organizations that do have senior developers whose voice carries a lot of weight in the company that will argue for good design and clean code and doing things the right way rather than just rushing every product out. Unfortunately, there's often a ton of management pressure because management can see the current deadline slipping and they can't see the price you're going to pay for that in technical debt down the road, for price you're going to pay for rushing things through. But again, I would argue for trying to create such a position, maybe informally versus formally, that if you're a person who cares about design, I would argue start exerting yourself and see if you can get more people interested. If your company doesn't already do code reviews, start your own informal code reviews, even if they're not required for everybody. Find a few other people like yourselves who care about design and start code reviews on your own. And you may find that it catches on.
Yeah, I just wanted to add, I haven't worked in developing that long. I've been more in a sort of mixture of industries, film and other interactive things, but that role, that R&D role is pretty strong in that industry, where there is somebody whose job is to sort of improve. And I don't mean R&D as in the figuring out new and interesting ways of doing things, more just the improving of how you do things now as well, but really owning that responsibility. You mentioned like having a person, like maybe there's a senior developer who's really good at it. That's one thing, but actually having that role, having that responsibility as part of their role and something they're actually, when they go in for their talking about how they're doing with their work and everything, they're having their review, that's actually a part of the role. It's something that's paid attention and actually respected as well, not just I'll do it in my free time and I'm really good at it, so that's fine. So it's something I try and do with other companies to try and help them get this role in there. But it's interesting to see how much it's ingrained or not in developing worlds as well.
So I would say first, I think having a role like that is great, although the eventual goal is that everybody is thinking about design. If you just have one person, if only one person in an organization is thinking about design, it's a losing battle. But
yeah, that's not what I meant. It's more the person to own the group
to have the evangelist
effort. Yeah, it's to sort of help get other people on board,
sets the
push
tone.
other people to do that, but actually own that responsibility and then be the one to fight with the producer over the battle of time and that as well. So
it needs to be somebody who walks the walk. It doesn't just talk the talk. They need to, they need to be willing to spend their own personal time going in and fixing little nitpicky things in order to make the design better.
I will add that as a senior developer, you got to have pretty thick skin, because when you come in and do code reviews, invited or not, when you start from the basics of even variable name consistency and spelling errors, is that the value of a senior level developer? Maybe not, but when you first come in, there's a big barrier of entry. That's all.
Yeah, so I tell the students in my class, be prepared to receive criticism this quarter. I tell them, I'm going to be super nitpicky. I'm going to criticize every little thing. And you may think I'm being nitpicky, and you're right, I am being nitpicky, but it's important for you to get in the mindset where you just do this stuff right from the beginning.
I kind of had as we're going through this, I kind of had this funny image in my mind, and I was thinking about, of all things, like the U.S. soccer team. And over the last few years, like the USA has wanted to improve their soccer team, but it's just one of those things where good soccer teams come from countries that have culture that play a lot of soccer, so they're good because it's at a grassroots level, right? And it feels a little similar to this, where you're one professor at one university teaching 18 students. How do you build a movement that would like propagate these ideas? It feels like because we're programmers and because we can do things like this, we should be able to move it forward. But it still feels like, how do you give this movement momentum, right? Like that is fundamentally the issue here. And also, I would think that the fragmentation of the ideas of what a good code is, like we said at the beginning, right? So there's kind of two things at play. What constitutes a good idea, and then how you move that, you agree on one and move it forward, I guess, right?
So first thing I would say is refuse to despair. It may seem like I'm just one person. What can I do in this horrible world? I'm just going to go along with things. And so my first thing is no, stand up for what you think is right and talk about it. And it's possible you won't be able to convince enough people to really make change, but you should still do the right thing. So that was how I started off in the class. I figured, maybe these ideas will all die when I die. That'll be the end of it. They'll all just fizzle out. But I figured I'm going to do it anyway. And of course, writing the book was one way also to reach a wider audience. I'm hoping that will catalyze more and more people thinking about this. For me, the next step would be to somehow figure out a way to transplant this class so that other people can teach it. Not sure quite how to do that, given that most faculty don't have, they don't have the experience that I have. But I actually think if someone was brave enough as a professor, and they just taught the class, even not having that much experience, but used the book and did the code reviews, after teaching it once or twice, they would begin to recognize the issues themselves in the code reviews and be able to do a job probably just about as well as I can. But it would take them, they'd have to admit they don't know squat at the beginning and just gut their way through the first offering or two to figure things out. And it'd be a serious learning experience for the professor, but they'd be able to figure it out. But if you have any other ideas about how do we make this happen in the whole community, I'd be curious to hear about it. But I refuse to despair. I still believe I'm unwilling to give in and just accept bad design in our field, because I don't think it needs to be that way.
Okay, if there are no more questions. I'd like to thank Professor for the amazing presentation. We wish we can all clap, and maybe we'll save this video and then force everybody to watch it every week before starting the week, like between 9 to 10. All the developers should watch this video. This is the case about the book. So you can read it once and it's short, and that's why you should read it again and again and again. All the concepts, new ideas come every time you read it. So thank you very much for writing the book in the first place. Thank you for working on this, and thank you very much for joining us tonight.
Sure, happy to be here. And again, I'm always interested in new ideas, and I'm happy to receive criticism as well. So if you have any thoughts, drop me an email or post on the book mailing list.